Assalamualaikum and a very good day I bet to all the coordinators that are watching this video. Today, we are from Group 4-2 will be presenting the hydrocracking of vacuum distillate to produce gasoline and other fuels. Hello, as for the introduction, our group will be presenting about the hydrocracking process of vacuum distillate into gasoline and other fuels. In general, hydrocracking is defined as a process in which the components of gas oil are converted into lighter molecules under the influence of hydrogen gas and the presence of a catalyst. Fluid catalytic cracking is also categorized under the same hydrocracking process. It is widely used to convert high boiling and high molecular weight hydrocarbon fractions of petroleum crude oil into more valuable gasoline. For the vacuum distillate, it comes from the vacuum distillation, where it is a part of refining process that helps to produce petroleum products out of the heavier oil left over from atmospheric distillation. The distillation column is under a vacuum, so it is significantly less than atmospheric pressure. Hence, at low pressure, the boiling point of atmospheric distillation unit bottom is low enough that lighter product can vaporize without cracking or degrading the oil. Vacuum distillate consists of several types of gas oil such as jet fuel, kerosene, and diesel, which are slightly heavier than the middle distillate.
Catalysts used for hydrocracking are bifunctional, as they comprise a hydrogenation-dehydrogenation function provided by metals and an acidic function given by the support. The metal function is typically provided by noble metals, for example Pt, Pd, or a combination of group MOW and group NiCO metals in their sulfide state. The acidic support might consist of amorphous silica alumina, a zeolite, or a combination of zeolite and amorphous oxide. These are the comparison between silica alumina and zeolite. For zeolite, it has higher activity than owing to a higher acid strength compared to silica alumina and have a higher thermal or hydrothermal stability compared to silica alumina. For silica alumina, it has a high cooking rate compared to zeolite. We have chosen zeolite-based catalysts, and we have focused on three catalysts, that is NIMO MCM41, NIMO ASA, and NIMO USY. We have done a comparison for the characteristic of these catalysts. The first one, selectivity. NIMO MCM41 catalyst presented a selectivity to middle distillate intermediate between that of NIMO or ASA and NIMO USY. For activity, NIMO MCM41 catalyst showed a higher activity than NIMO SA and NIMO USY. For hydrodesulfurization (HDS) and hydrodenitrogenation (HDN), catalysts based on MCM41 provide better HDS and HDN activities than those based on ASA and USY. Below are the tables that show the conversion for these catalysts.
Hello, I will explain about the reaction mechanism. There are a few types of catalytic reaction operation. The first one, hydrotreating. Second one, hydrocracking. Third one, catalytic reforming or catalytic cracking. The fourth one, non-catalytic reaction operation such as thermal cracking. And the last one, treatment operation such as the removal of impurities and fine fractionation. FCC in refining industry. Figure 1 shows the role of FCC in the refining industry. In refining industry, it produces LPG, naphthas, kerosene, and diesel oil. The VGO, a wide range of feedstock, can be processed in FCC units, such as hydrotreated gas oils, cracker gas oils, and the aspartate oils. Figure 2 shows the schematic of FCC units. In fluidized catalytic cracking processes, high molecular weight hydrocarbon liquids and vapor are contacted with hot, finely divided solid catalyst particles either in a fluidized bed reactor or in an elongated transfer line reactor and maintained at an elevated temperature in a fluidized or display state for a period of time sufficient to effect of desired degree of cracking to lower molecular weight hydrocarbons of the kind typically present in motor gasoline and distillate fuels. Figure 3 shows that the schematic on how the process breaks high boiling straight chain alkanes hydrocarbons into smaller straight chain alkanes and branch chain alkanes such as alkenes and cycloalkanes. Large hydrocarbon molecules breaking down into smaller molecules can be referred to as the scission of carbon-to-carbon bonds.
Determination of basis for reactor design. In most case studies, to design a reactor is basically to determine the basis before reaction process. The basis in engineering is the main key to produce a desired or undesired product according to the set parameters as specified conditions and reaction rate. The operating conditions are required based on the reactants, catalyst, and the type of reactor used. In this study, our group have decided to use a fluidized bed reactor, and we use the FCC, which is the fluid catalytic cracking unit. As you can see in the slides, the general conditions of FCC unit are inserted as seen in the slide. But the main condition of this FCC unit is it operates at temperature approximately 500 to 550 degrees C. To validate the determination of basis for reactor design, a researcher did propose a 4-law model for cracking of vacuum gas oil (VGO), and in this research study, a coke is independently considered as a lump. Since FCC reactor operates at a very high temperature, the secondary cracking reactions occurs for gasoline to form coke and light gas. This is the experimental equipment set up for FCC in a fluidized bed reactor, and during the experiment, several runs were performed. As you can see, this is the input and output laboratory experimental data, and the description of the first row and the last row of the table are shown as in the slides. Proceeding to the next slide, this slide shows 3 different graphs with 3 different temperatures, which are the temperature from 450, 480 to, and the next slide will show the graph of 490 degrees C. For the first graph, it is the ASTM distillation curves for VGO, feed and product at different temperatures. Compiling all the graphs of ASTM distillation curve, we can summarize that the determination basis for reactor design, a 4-lump-based kinetic model, is appropriate for FCC VGO in a fluidized bed reactor. The highest temperature was chosen as it would produce more light gas, and as mentioned earlier, the common temperature for FCC unit is 550 degrees C, so 490 degrees C is the most appropriate temperature to be used. For the graphs below are the conversion of cracking reaction at different temperatures, and the maximum conversion reached is 40%.
So this is the reactor selection and reactor design. So as mentioned by the previous presenter, we are using fluid catalytic cracking FCC setup, which consists of this fluidized bed reactor. This fluidized bed reactor is designed with stainless steel 347 and being equipped with targeted feed storage tank, burette, reciprocating pump, feed preheater, feed nozzle, double pipe, and also double pipe condenser, and also 3 traps. So the system used for this fluidized bed reactor is 4-lump model system, which consists of these 5 reactions: vacuum gas oil converted to gasoline, vacuum gas oil to light gas, vacuum gas oil to coke, gasoline to light gas, gasoline to coke. So the regeneration process that we can achieve in this project is when the coke formation occurs as a side reaction, which deactivates the active sites of the catalyst through poisoning or blockage or both. This will result in activity loss of the reaction. So this FCC catalyst will circulate between the riser of the reactor and regenerator vessels continuously. So this coke will then be converted into other compounds, which are CO, CO2, H2O, SOX, and NOx compounds. So these are the overall reaction equations as being explained detailed in the report. So for this For destruction, we have for gas oil, for gasoline, for light gas, C1 to C4 for coke, and catalyst deactivation rate.
As for the summary, based on our research, catalyst NIMO is the most suitable catalyst that have better activity, stability, and conversion compared to other catalysts. The catalyst used is to promote the breaking of the large molecule so that it can maximize its yield of gasoline. Most of the cracking occurs through a bimolecular beta scission as the obtain high yields of branch products. Fluid catalytic cracking (FCC), which consists of fluidized bed reactor, is applying for lump system. And for the basis for this reactor design is temperature reaction is 490 degrees Celsius, while the conversion is 40%.